This is AB Calculus, the fourth 6 weeks final. We have some problems we're going to go over here. This problem, first one, the function g has a first derivative given by g prime of x equals 20x plus 1 times x times 20x plus 2 squared. At what values of x does g have relative minimum? Well, we have a relative minimum where g prime of x, or we have critical numbers where g prime of x equals 0. And so we're going to say 0 is equal to 20x minus 1 times x times 20x plus 2 squared. And so using zero factor property, we know that we have a critical number where x minus 1 is equal to 0, where x is equal to 0, and where x plus 2 is equal to 0. So solving for x, we have x equals 1, x equals 0, and x equals negative 2. So these three numbers are what we call our critical numbers. And we can do a number line analysis with these critical numbers at x equals negative 2, at x equals 0, and at x equals 1. And up here we put above the line g prime and below g, and we do a sign analysis. And the reason sign analysis is helpful because of this little chart, this f prime, f double prime that I'm putting here at the upper right. We have plus, minus. I hope you've seen this in your class. And let's see, we have concave up, concave down. And so on the f prime row, we have plus, minus, increasing, decreasing. And then the last row, the f double prime, we have plus, minus. And what we're interested in here is we can see how increasing and decreasing is related to f prime being positive or negative. And so we're going to evaluate all these intervals here, and then we're going to use this factored form. And I hope we can see that if x is anything besides negative 2, this factor of x plus 2 is always going to be positive because of this squared. We have a multiplicity of 2. And so if we go to the left of negative 2, we're going to have negative times positive. So we have g prime being positive, which means g is increasing over that interval. If we go between negative 2 and 0, we still have negative, negative, positive. So we are still, g is still increasing on this interval. And to the right of 0, well, we're going to have, the sign would change here to be negative, and then this would be, actually to the right, this would be positive, and this would be negative. So we have negative times positive, negatives will be decreasing. And then to the right of 1, we would be positive all across the board. So we can visually see that we want to find where we have relative minimum, well, where we're going to change from decreasing to increasing. So let's say relative, I'm going to put my justification here, minimum at x equals 1, because g prime changes from negative to positive. So that's going to be our answer. Next, 8. Let f be the function fx equals 4 to the x power. Estimate the integral from 0 to 2 of f of x dx. Well, we want to find 4 equal subintervals, so we can just write this. Estimate of 0 to 2 f of x dx is equal to, we can just put 4 blanks here. So we have that. Now, to find the delta x, well, what we're going to have is we want 4 subintervals. So delta x is going to be our b minus a, or 2, divided by the number of equal subintervals. We're going to have 1/2. So each of these intervals here, these rectangles in a Riemann sum, is going to be multiplied by 1/2. Okay, now we need to find the height of each of these 4 rectangles, and to do that, we can create a little table down below where I'm going to put x, f of x, and we're going to have 0, x equals 0. These are 1/2 apart, delta x 1/2 apart, so we want 1/2, 1, then 1.5, or 3/2, and 2. Now if we plug in 0 to this function, f of, I'm just going to write here, f of 0 is equal to 0. So we have f of x 0 here. If we plug in 1/2, let's see, we get f of 1/2 equals 4 to the 1/2, which equals square root of 4, which equals 2. So 2 goes there. If we plug in 1, f of 1 is going to be 4 to the 1, which equals 4. So 4. If we have f of 3/2, that's going to be it'll be it'll be 4 to the 3/2 power, which equals square root of 4 cubed, which equals 2 cubed, which equals 8. So that's 8. And then we have finally f of 2 is going to be equal to 4 to the 2nd power, which is 16. Here we have 16. And so using a right Riemann sum, we're going to take this value on the right. So the one that goes here is 2, then 4, then 8, then 16. And we don't really have to simplify beyond that. We could if we wanted to. Let's go on to problem 9. The derivative of x minus 2 over x squared plus 1. Well, here I recommend using the quotient rule. And to do that, if we take the high value here in the numerator, we're going to get x minus 2. The derivative of the high is equal to 1, and low is equal to 2x. Excuse me, I'm a little distracted here. Low is equal to x squared plus 1. D low is equal to 2x. So now we can just start writing this out. I'll put low-de, 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 high. And what's low? X squared plus 1. Low-de, 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 high. And high is 1, so that's multiplied by 1, so we're not going to put it together. Minus high. D high, D low. And D low is 2x. All over low squared. And start quite high enough. And then we can go ahead and simplify this out, kind of combine like terms, but that's essentially going to be it. Let's go on here. 10, for the function h of x equals 2 square root of x, what is the average rate of change of the closed interval 0 to 4? Well, average rate of change equals f of b minus f of a over b minus a. And so we can just define 0 is A and 4 is B. So h of 0 is going to be 2 square root of 0 equals 0. H of 4 is equal to 2 square root of 4 equals 2 times 2 equals 4. So A rock is going to be equal to f of b minus f of a over b minus a, which equals 1. So that's our value of A rock, 1. Next, for the function h of x equals 2 square root of x over the closed interval 0 to 4, what is the value of x that justifies the conclusion of the mean value theorem? So that's really a continuation from problem 10, isn't it? So what we're going to do is find the instantaneous rate of change, but first we're going to set h of x equal to 2 x to the power of 1/2, because that's what the square root is. So h prime of x, taking our first derivative, is equal to 2 x to the 1/2 minus 1, or negative 1/2, times 1/2. So we could have multiplied the 1/2 first, but the 1/2 and 2 will cancel each other. What we have left is x to the negative 1/2 power, which equals to 1 over square root of x. So what we want to do now is take from our previous problem, we found that A rock was equal to 1. So we can set 1 equal to 1 over square root of x. And if we cross multiply the square root of x, we have square root of x is equal to 1. And so x is equal to 1 squared, which equals 1. So that's it, x is equal to 1. So x equals 1, and we'll say satisfies conclusion of MVT. Next, 12. What is the equation of the tangent line to the graph of the function fx equals x cubed, where x equals 4? Well, to get a tangent line, we need first a point, and then we need a slope. And our point is going to be the x-coordinate 4, and then the y-coordinate, whatever we get. It's going to be x1. So f of 4 is equal to 4 cubed, which equals 64. So there's 64. That's our y1. And then our slope. Well, let's find f prime of x. That's going to be 3x squared. And we want to find f prime of 4 to find our slope. So we get 3 times 4 squared, which equals 16 times 3, or 48. So we'll say m sub t equals 48. So our equation is y minus 64 equals m, and m is 48 times x minus 4. And that's going to be our answer. Next, we get into the kind of free response section here. The velocity of a particle moving along the x-axis is modeled by a differential function v, where the position x is measured in meters and time t is measured in seconds. Selected values vt are given in the table above. The particle is at position x equals 7 meters when t equals 0 seconds. Estimate the acceleration of the particle at t equals 36 seconds. And so 36 is going to reside here between t equals 32 and 40, meaning that we're going to want to use these two values. Now, acceleration can be estimated as the average change of velocity. So, estimate of A of t equals the average rate of change of velocity, v of t. And for that, we're going to get f of, or I said f, v of 40 minus v of 32 all over 40 minus 32. And so we have here v of 40 is 7, and v of 32 is negative 4, so we have minus negative 4 over 40 minus 32, so 8. So what we get is 11/8. And that's going to be, what is our unit? Well, that's going to be meters, not per second, but per second, or second squared. So that's going to be that one. Using correct units, explain the meaning, okay? The meaning of the integral from 2040 v of t dt. Well, the meaning is going to be amount, right? The integral of a rate is an amount. So, explain the meaning, estimate of v of t dt is an estimate of the number of meters traveled, right? Or actually it's going to be the displacement, the distance covered from 20 to 40 seconds. I don't know if I had anybody who really gave a good meaning here. Use a trapezoidal sum with the three subintervals indicated to approximate. So estimate of 20 to 40 v of t dt is equal to 3. There's 1, 2, 3. And so our delta t here is 25 minus 20. But for a trapezoidal sum, we're dividing by 2. So I'm just going to put the 2 here. And then we're going to have the height of each of these trapezoids. Well, it's going to be 25 minus 20, or 5. Okay, I'm going to put this here. The next ones we have is 32 minus 25, or 7. And the last one is 40 minus 32, or 8. And now what we do is take base 1 plus base 2. Well, our base 1 is going to be negative 10 plus negative 8. So you can put negative 10 minus 8. The next one we're going to have is -8 plus -4. And the last one we're going to have is -4, which are base 1 plus 7, or base 2. So that's going to be it right here. Next, C, for t between 0 and 40, you must particle change direction in any of the subintervals indicated by the data in the table. If so, identify the intervals and explain your reasoning. If not, explain why not. So, yes. Twice. What we have is we change direction where we're changing the velocity from positive negative, or negative to positive. And so since 0 is greater than v of 20, and less than v of 8, according to IVT, particle change direction, or had to change direction. And also, since 0, now we're looking at this interval between t equals 32, t equals 40, 0 is greater than v of 32, but less than v of 40. Again, according to IVT, particle change, or what change is, direction. Okay, the last part, and this is one that I don't know if anybody got to. Suppose the acceleration of the particle is positive for t between 0 and 8 seconds. Explain why the position of the particle at t equals 8 seconds must be greater than x equals 30 meters. Well, first of all, we know from the text is the particle starts at 7 meters. Okay, when t is equal to 0. Now, if we have acceleration being positive, that means that the value has to be, this v of t has to be continuously increasing all the way up to 8 seconds. So since v of t is increasing on 0 to 8, the distance covered has to be greater than 8 times 3. If we do a Riemann sum here, right, a left Riemann sum, 8 times 3, which equals 24 meters. And since 7 plus 24 is greater than 30, position of particle is greater than 30 meters away. So that's just using the logic, and really I had to descend into a verbal description essentially from the values. But this is the way you're going to be needing to articulate properly on your AP exam. Now this last free response section, a function g of x is continuous on the closed interval from -1 to 5, and its first and second derivative are shown in the table below. Find the x values of all local extrema on the graph of g of x and tell which are maxima and minima. Well, for that, we can use, for supplementary analysis, our number line. I think I'm going to put it right below so I can go right below. So we can mark here at x equals -1, and we have x equals 2, we have x equals 3 here, x equals 4, and x equals 5. And we're going to put g prime above and g below. So to the left of -1, that isn't of any consequence. We don't know that. But between -1, x equals -1 and 2, we have a negative sign, meaning that g is decreasing in that interval. Again, it's back to this f prime, f double prime chart that we looked at, right? Plus, minus, increasing, decreasing, concave up, concave down. And then we have plus, minus, increasing, decreasing. And then in the final row, we have plus, minus, f double prime. Now, between 2 and 3, g prime is also negative. So g is decreasing on this interval. Between x equals 3 and x equals 4, we have g prime of x is positive. So we are increasing here. And then finally, between 4 and 5, we go back to g prime being negative, so we are decreasing. So we have local extrema at x equals 3 and also x equals 4. Okay, and we have, which are maximum minimums, we have relative, first we're going to look at is this minimum at x equals 3, that's not -3, it's equals 3, equals 3 because g prime changes from, we have negative to positive. Okay. Next, we have relative max at x equals 4 because g prime changes from positive to negative. Next, tell where the graph of the function g of x is concave up or concave down. Justify your answers. So, similar thing here, except we're going to take these critical numbers here, and this time we have g double prime above and g below. And so we're looking at these changes here. So between, we have -1, 2, 3, 4, and 5. Okay, between -1 and 2, negative. So we are concave down in that interval. Between 2 and 3, we have f d double prime being positive, concave up. Between x equals 3 and x equals 4, we have negative, so we're concave down in this interval. And finally, between x equals 4 and x equals 5, we have f to g double prime being negative, so we have this. So we say concave down on, what are the intervals? Well, we got 3 of them. We got -1 to 2, union 3 to 4, union 4 to 5, because g double prime is less than 0. We have concave up on only one interval, 2 to 3, because g double prime is greater than 0. And then tell where the graph of the function g of x has points of inflection. We have points of inflection where concavity changes from either negative to positive or positive to negative, and that occurs twice. So we have points of inflection at x equals 2 and also x equals 3, because g double prime changes. You can say changes signs. I'd like to say from positive to negative, or from negative to positive. If g of x is a function of particles positioned along the x-axis, over what intervals is the particle slowing down? Justify your answer. Well, for slowing down, we have to have opposite signs. And so here, between x equals 2 and x equals 3, we have the g prime being positive, but g double prime, g prime's being negative, but g double prime is positive, opposite signs. And also between x equals 3 and x equals 4. So slowing on 2 to 3, and also from x equals 3 to 4. And why is that? Because g prime and g double prime have opposite signs. And that's going to get us through all we have. I hope this has been helpful to you. Good luck, and thanks for viewing.